Yes. Okay, fine. So today we are going to discuss about the two topics, that is the relation between the parameter sets and interconnection of the two port networks. So in that, okay, first let me start with the first topic, that is the relation between the parameter set. So first let me discuss about the relation between the parameter sets in that the Z and Y parameters. So what is the relation between the Z and Y parameters? Okay. So as we know, we got the Z and Y parameters from the voltage and current equations. So because here these equations represents the Y parameter equations, because in the Y parameter those are the admittance parameters. So we have to write the current equations in terms of the voltage, that is I1 I2 in terms of V1 and V2. So and Z parameters we have to write the voltage equations in terms of the current. So because these are already we have discussed in the last lecture. Okay, so like these two are the voltage equations for the Z parameters. So here I am going to find the Z parameters in terms of Y, or the Y parameters in terms of the Z parameters. Okay, so here suppose let me consider these two equations. Let me consider this is equation A. Okay, so that is V1 and V2. So these are the two equations. Okay, these two equations having the two variables, because here we are going to find I1 and I2. Okay, so let me consider I1 and I2 are the variables. Okay, so because the independent variables, and V1 V2 are the dependent variables, so now we are going to find I1 and I2 by solving these two equations. So if you want to solve these two equations, we can apply the Cramer's rule. Okay, so here I'm going to apply the Cramer's rule to find I1 and I2. So to find the Cramer's rule, because you know how to represent these equations in the matrix form, because we have already discussed in the last lecture. So here if you want to find the determination of this Z, because here Z11, Z12 and Z21, Z22 are the coefficients of these variables. Okay, so then the determinant of Z is, that is the determinant of Z11, Z12, Z21 and Z22. Then if you want to find I1, then what you have to do, just you have to replace the first column by these variable, these constants, because here usually the equation is like ax plus what is that by equal to c, or like a1 x plus b1 y, okay, is equal to c, or like that this is the equation. So here c is the constant, so which means here v1 or v2 are the constants. So then we have to replace the first column with this v1 and v2 divided by the determinant of the total matrix, that is delta z, then you will get the I1. So if you simplify this, the determinant, that is V1 into Z22 minus V2 into Z12 by delta z. Then if you simplify this, then you will get I1 is equal to Z22 by delta z into V1 minus Z12 by delta z into V2. So let me consider this is equation number B. So similarly, if you want to find this I2, then again what you have to do, you have to replace the second column with V1 and V2, and again you have to substitute in this equation, that is I2 equal to the determinant of this matrix divided by delta z. Then the determinant of this one is again, that is AB minus B, sorry, what is that, AC minus ABC, so AD minus BC. So that is Z11 V2 minus Z21 V1 by delta z. So if you simplify again this one, then you can write this equation as I2 equal to, because here just Z11 by delta Z into V2 minus Z21 by delta Z into V1. So let me consider this is equation number C. So if you observe here, this is I1 and I2. This I1 is equal to Y11 V1 plus Y12 V2, and I2 is equal to Y21 V1 plus Y22 V2. So here similarly, the equation B and C also represent I1 and I2, and these two equations also represent I1 and I2, right? So if you compare these two equations with B and C, so see here it is also, what is that, V1 V2 and V1 V2. Here is also the variables are V1 V2 and V1 V2. Okay, so then you can just compare what is there in the place of y11 and what is there in the place of y12. Then if you observe, see, these are the current equations. We have considered D. Then if you compare these BC with the D equation, then in the place of y11 you are having z22 by delta z. See, this is z22 by delta z here, because the in the admittance the current equation is I1 is equal to y11 into v1 plus what is that, y12 into v2. So in the place of y11, what is there here, that is z22 by delta z, and in the place of y12, what is there here, z12 by, sorry, minus z12 by delta z. So like that, this is z12 by delta z, this is y22, and similarly sorry, y12. So similarly the y22 and the y12. So like that, we can find the relation between z and y parameters. So if you write these equations in a matrix form, then y11, y12, and y21, y22. So here in the place of y11, what you are having, that is z22 by delta z, and in the place of y12, what you are having, that is minus z12 by delta z. So similarly y21 and y22. So now this is how we can find the relation between the different parameter sets. So that is the relation between, this is the relation between the y and z parameters. Okay, and then similarly, if you want to find, this is we are representing the y parameters in terms of the z parameters. Suppose similar way, if you want to represent the z parameters in terms of y parameters, just you apply the reciprocal, then you will get the z parameters in terms of the y parameters, because as we know, the z is equal to 1 by y. Okay, so that's why just you have to apply the reciprocal to this one. Then because here, if you apply the reciprocal to the whole equation, then one which means 1 by y1 is nothing but z11, and 1 by y21 is equal to z12. So like that. So you can just simply I mean replace the letters in the place of z as a y and y as a z. Then you will get the relation between the z and y parameters, which means the z parameters in terms of the y parameters. So which means, suppose if you are having a two-port network, so if you want to find z and y parameters for that particular two-port network, so what you have to do, you have to find any one parameters first, whether the y parameters or the z parameters. Then after that, you can use this relation, then you can find the remaining parameters. Suppose if you are having a two-port network, so for the two-port network, you want to find y and z parameters. Then in that case, first you can find the y parameters, sorry, the z parameters. So after finding the z parameters, you can substitute in these equations, then you will get the y parameters. So like that we can find. So like that we can use these relations to find the different set of parameters for a given two-port network. So in a similar way, this represents the relation between z parameters and h parameters. So actually in the before case, this is the relation between z and y parameters. So here I have explained the proof also, but in the next coming the relations, I am not going to explain the proofs. But don't worry, those proofs are also very easy. Those are some mathematical equations that you have to solve. Okay, so don't worry, I will give you the material. So once you can go through, you will get understand, because those all are the equations. Okay, so that's why I mean I am not going to explain those proofs. Okay, but if you want, I can give you the, not if you want, I can definitely I will give you the material. So once you go through, then you will get understand. Okay, then so rule number 4a6, what you are doing, whether you are listening the class or doing something else. Then so here this is the relation between the h and z parameters. So which means, suppose if you want to represent the h parameters in terms of the z parameters, so similar like z and y parameters. So here h11 is equal to delta z by z22. So again here delta z is the determinant of the impedance matrix. The impedance matrix is nothing but that is z11, z12, and z21 and z22. That is the impedance matrix. So if you find the determinant of that impedance matrix, then that is represented by delta z. So H11 is equal to delta Z by Z22, and H12 is equal to Z12 by Z22. So similarly, H21 and H22 you can find by using this relationship. Then similarly, this equation will show the relation between the y and h parameters. So which means here the h parameters are in terms of z parameters, and here the h parameters are in terms of y parameters. Okay, so here similarly like here, so here h11 is equal to 1 by y11, and h12 is equal to minus y12 by y11. So similarly, the H21 and H22 also we can find by using these two equations. So here in similar way, this is delta Y is nothing but the determinant of the admittance matrix. So what is the admittance matrix? That is Y is equal to that is a 2 by 2 matrix, that is y11, y12, and y21, y22. So that is the admittance matrix. So the determinant of the admittance matrix is represented by these delta y. So like this, you can represent these h parameters in terms of the y parameters. So in a similar way, so this equation represents the relation between the ABCD and Z parameters, and the second equation represents the relation between ABCD and Y parameters. So which means here we are going to represent ABCD parameters in terms of the Z parameters as well as in terms of the Y parameters. So here also these are the different equations to represent these ABCD parameters in terms of the Y parameters. Okay, like this is A equal to Z11 by Z21 and B is equal to delta Z by Z21, like that. So in similar way, so this relation represents the relation between the ABCD and Y parameters. So which means here the ABCD parameters are representing in the form of Y parameters. So which means again here A is equal to minus Y22 by Y21 and B is equal to minus 1 by Y21. So in the similar way, this C and D represents these two equations. So and next the relation between ABCD and H parameters. So because there are mainly the three or four types of H parameters, those are Z, Y, H, and ABCD. Of course, there are two more also. Those are the inverse H and inverse ABCD. So here, because here see the ABCD parameters are representing in terms of the remaining three parameters. What is that? The Z, Y, and H. So in a similar way, H parameters, I mean the ABCD parameters are representing in terms of H. So that is A is equal to minus delta H by H21. So which means here delta H is nothing but what is that? The determinant of the H parameters matrix. So the H parameters matrix is that is H11. It is also 2 by 2 matrix, that is H11, H21 by H12 by H21 into H21 and H22. So that is the what is that? The H parameters matrix. So in a similar way, next there are the different relationships between all the different parameters. So here the g is nothing but the inverse H parameters, and t is nothing but the transmission parameters. Okay, don't get confused. T is are sometimes we representing the transmission parameters as a t, that is t11, t12, and t21 and t22. Are in some books they are represented as a abcd, that is what is that? A, B, C, D. Okay. So if you from this table you can find any parameters from any other parameters. Like suppose if you want to find Z parameters in terms of the Y parameters, then by using these equations you can find Z parameters from the Y parameters. Then if you want to find Z parameters from the H parameters, then you can find from these equations. This is Z and H. Okay. Then again, this is the inverse H parameters, the G parameters. Okay. The Z parameters from the Z parameters. That is the inverse H parameters. And again, the Z parameters from the transmission line parameters. So like this, you, again, Y parameters also you can find from Z, Y, H, G, T. Okay. The H parameters also you can find all other four, what is that? Of course, H and H is the same, 1, 2, 3, 4, all other four parameters. So like that, if you know any one parameters, you can find the remaining all other parameters by using these relationships. Okay. So this is the conversion table. So this is how the relation between the different set of parameters. That is what is that? So the Z and whatever it is, what is whether it is Z and Y or Y and Z. Okay, suppose if you want to, this represents the Z parameters in terms of Y, and if you want to know the Y parameters in terms of Z, then this is the equation. So like that, the relation between any two set of parameters you can find or you can define from this conversion table. Okay, so this is about the relation between the different set of parameters. Then when coming to the interconnection of the two port networks, so mainly there are actually there are 5 different types of interconnection of two port networks, but according to US syllabus mainly but in those 5 there are only basically there are only 3, but the remaining 2 are the combination of these 3 only. So we are not going to discuss about those what is that 5 I mean the remaining 2 parameters. We are going to discuss about the basic 3 interconnections. Those are the series connection and the parallel connection and the cascade connection. So you know what is series and what is parallel and what is cascade. The series is nothing but because the two terminals must, I mean, sorry, the one terminal must have the common node. So this is series, because we have already discussed about the series, I mean the series connection of the resistors and the parallel connection like that. Okay, so no problem, again we will discuss in detail one by one here. So first let me go for the series connection. So for the series connection, the best suitable parameters are the Z parameters. So here I have considered two-port networks, so that is ZA and ZB. So the first two-port network parameters are, we can consider as a what is that, Z11A and Z12A and Z21A and Z22A. And similarly for the second two-port network, the parameters are, we can consider as a Z11B and Z12B and Z21B and Z22B. So here these two are connected in series. Okay, then the resultant network for this series connection is this. So which means here we are going to find the resultant network parameters, that is Z. Okay, in terms of the, what is that, the network parameters of the two-port network 1 and the network parameters of the two-port network 2. So here let me consider for the first two-port network, that is ZA. So the input voltage is V1A and the input current is I1A. Similarly, the output voltage and current are V2A and I2A. So here for that network ZB, so the input current and voltages are I1B and V1B. So output voltage and currents are what is that, I2B and V2B. And the resultant voltage of the series connection is, let me consider V1, and the output voltage is V2. Okay, so and the currents are I1 and I2. So first let me consider the network ZA. So for that, if you take the network ZA, so as we know, because these are the Z parameters, so the in the Z parameters, the voltage equations are representing in terms of the current. Okay, so that's why here I have written, because here the voltage equations, what are the voltages for the ZA network, V1A and V2A. So that's why here I have taken V1A and V2A. Then what are the parameters that we have considered for that network ZA? Those are Z11A and Z12A, Z21A and Z22A. Then again, what are the currents for the network ZA? This is I1A and I2A. So that's why I1A and I2A. So similarly, these are the in a equation form, and this is in a matrix form. So similarly, if you consider for the network ZB, for this network ZB, so for that network ZB, also we are going to write these voltage equations in terms of the current. So the voltage of these networks ZB are V1B and V2B. So that's why here we have written V1B and V2B, and the currents are I1B and I2B, and these are the network parameters for the network ZB. So let me consider, this is equation number 1, 2 for that with respect to the network ZA, and these are the consider equation number 3 and 4 with respect to the network ZB. Then the condition for the series connection, as you know, because in the series network, the current flowing through the series elements is same. So which means here this is IA equal to, sorry, I1A equal to I1B equal to I1, right? Because this is the total current flowing through this one, and the current flowing through this network ZA is I1A, and the current flowing through this network ZB is I1B. So that's what here I1A is equal to I1B is equal to I1. So in a similar fashion for the secondary side, is also this I2A is equal to I2B is equal to I2, because these two are connected in parallel. Sorry, these two are connected in series. So in the series connection, the current flowing through the series elements is same. Okay, and similarly, but the current is not same. Okay, the current is, that is V1 is equal, sorry, not current, voltage. The voltage is not same, because the V1 is equal to V1A plus V1B. This is the rule that we have already discussed in the first and second units. Okay. So like this, these are the conditions for the series connection. These are the general conditions, not only for the two-port networks. Okay, these are the general conditions for the what is that series connection. So from these conditions, so we can find the total impedance of the equivalent circuit. So that is, so here this is the equation number V1 and V2, because you know this is the equivalent circuit. For this equivalent circuit, the voltage is V1 and the output voltage is V2, and similarly the input current and output currents are I1 and I2. So if you want to write the equations for these equivalent what is that two-port network, so here also we have to write the voltage equations in terms of the current, So which means here in the place of V1B and V2B, we have to write V1 and V2 because the input current is V1 and the output current is V2. And similarly, in the place of I1B and I2B, we have to write I1 and I2. Okay. So like that here, these are the two equations. So V1 is equal to V1A plus V1B and V2 is equal to V2A plus V2B. These two are from the series connection condition. So here, if we take the equation number 6, that is V1 is equal to V1A plus V1B. So here in equation number 6, that means from equation number 1 and 3, you can get V1A and V1B. See, this is V1A and V1B from equation number 1 and 3. So you can substitute the V1A and V1B from equation number 1 and 3 in equation number 6. So here I have substituted, that is Z11 into I1A and plus Z12 into I2A in the place of V1A, and in the place of V1B, so Z11B into I1B plus Z12B into I2B. So as we know from this condition, this is I1A is equal to I1B is equal to I1, and I2B is equal to, sorry, here this is I2A, not I2. I2A is equal to I2B is equal to I2. So that's why here in the place of I1A and I1B, I have substituted I1 and I1, and in the place of I2A and I2B, I have substituted I2 and I2 from this equation number 5. Okay. Then if you simplify this equation, if you take I1 as a common, then you can simplify this equation, that is V1 is equal to Z11 into A plus, sorry, Z11A plus Z11B into I1 plus Z12A plus Z12B into I2. So here, before continue, I just want to remind you that after 10 minutes, this class will going to end. After that, I will again send you the link so you can join in the second link, because as you know, we can record this class up to 40 minutes only. Okay, fine. So then,
So with the same link we can join, sir.
yeah, the same link. Okay, the same link. By using the same link, you can join. Okay, once it is get disconnected, then you can join again by using the same link. Okay. Then similarly, if you take the equation number 7, this is V2 is equal to V2A plus V2B. So you can substitute the value of V2A and V2B from this equation number 2 and 4. Okay, then from equation number 2 and 4, you can take that V2A and V2B and substitute in this equation number 7. Then you will get the equation number V2. So this is the equation number V2. After simplifying like this equation number V1, so if you simplify, then you will get the equation number V2 is equal to Z21A plus Z21B into I1 plus Z22A plus Z22B into I2. So if you observe these equation numbers, that is, this is equation number V1 and this is equation number V2. So these are in the form of V1 plus Z11 into I1 plus Z12 into I2. And similarly, V2 equal to Z21 into I1 plus Z22 into I2. Right? So which means we can write these equations like V1 is equal to Z11 into I1 plus Z12 into I2, and V2 is equal to Z21 into I1 plus Z22 into I2. So which means the Z11 is equal to Z1A plus Z11B, and Z12 is equal to again Z12A plus Z12B. So similarly Z21 and Z22. So which means, suppose if you want to find the equivalent, what is that, two-port network circuit impedance, that is Z, then you have to add the impedance matrix of the network ZA and the impedance matrix of the network ZB. Then you will get the equivalent impedance of the equivalent two-port network. So this is how the series connection. So which means here you have to remember the two things. One is, for the series connection, only the Z parameters are most suitable. Okay. So then if these two are in series, then what you have to, if you want to find the equivalent circuit impedance, then you have to add the impedance matrices. Then you will get the equivalent circuit impedance. Okay. So this is proof. Okay. But finally, what you have to remember? You have to remember this thing. Okay. So in similar way, if there are three networks connected in series, then you have to add like ZA plus ZB plus ZC. Okay, the what is that, the Z parameters of the third network also you have to add. Then you will get the resultant Z parameters of the equivalent network, the equivalent two-port network. Okay, so this is about the series connection of the two-port networks. Then when coming to the parallel connection, okay, maybe the remaining, okay, 6 more minutes, so maybe you can finish this parallel connection too. Okay, let me try to finish the parallel connection in 5 minutes. So in the parallel connection, so these y parameters are most suitable for the parallel connection. So here I have taken the two networks. Let me consider that is ya and yb. So these two I have connected in the parallel way, and this is the resultant network or the equivalent network of these two parallel networks. So that is I am representing as a y. Then similar way in the, like in the series connection, so in the parallel connection also, here we have taken the y parameters. So y parameters, so in the y parameters we have to write the current equations in terms of the voltage. So that's why here I have written this is I1a I2a is equal to this I mean in terms of V1a and V2a, because for this first network, for that ya network, here the voltage and currents are, here the voltages are V1a V2a and the currents are I1a I2a, similar like in the series connection. So that's why here I have written the equations, the current equations in terms of the voltage for the first network, that is ya. So similarly for the second network yb, again we can write what is that I1b and I2b in terms of V1b and V2b. So these are the current equations in terms of the voltage for the second network, that is yb. So then the condition for the parallel network, so similarly in the series network the currents are same and the voltages are not equal, but here the voltages are same but the currents are not equal, because these are in the parallel connection. So in the parallel connection the voltage is same, because what is that, if the two resistors are in parallel, then the voltage across those two resistors are in same, but the current is not same, because the current is like I is equal to what is that I1 plus I2, because if you take the total current as I, and the current flowing through the first resistor is I1 and the current flowing through the second resistor is I2, then if those two resistors are in connected in parallel, then I is equal to I1 plus I2. So in a similar way here, for the two networks, for that first network the voltage is V1a and the second network the voltage is V1b, and if we consider the total voltage is V1, then the voltage V1 is equal to V1a is equal to V1b. So similar fashion for the second network also the voltages are same, because these two are connected in parallel. And when coming to the currents, so here this I1a is the current flowing through the first network, that is the input current, and this is I1b is the input current that is flowing through the second network. So that's why here this is I1 is the total current. So that's why here I1 is equal to I1a plus I1b, and similarly I2 is equal to I2a plus I2b. So here if you take these two equations, in I1 is equal to I1a plus I1b. Okay, so here I1a plus I1b, so here from these two equations, here this is I1a from equation number 1, and from equation number 3 this is I1b. If you substitute this I1a I1b in this equation I1, so here I have substituted in the I1, so in the place of I1a you can write this one, that is y11a into v1a plus y12a into v2a. Then similarly in the place of I1b you can write this equation, then you will get the equation like this. Then again you can replace here what is that, v1a equal to v1b equal to v1. So which means here v1, in the place of v1a you can replace by v1, because v1a is equal to v1. Similarly v2a as v2 and v1b as v1 and v2b as v2. So I have substituted here. So then after simplifying you will get I1 is equal, because you can take v1 as a common and v2 as a common. So if you take v1 as a common, you will get y11a plus y11b into v1, and y12a plus y12b into v2. So let me consider this is equation number 6. So in a similar fashion, I2 is I2a plus I2b. So you know what is I2a and I2b from equation number 2 and 4. So from equation number 2, this is I2a, and from equation number 4, this is I2b. So you can substitute this I2a and I2b in this equation number I2. So then you will get the I2 is equal to y21a plus y21b into v1 plus y22a plus y22b into v2. So again, if you write the y parameters equations of these equivalent, what is that, the two-port network, the series, the parallel equivalent to two-port network, then those equation are I1, I2 is equal to y11 v1 plus y12 into v2 and y21 v1 plus y22 into v2. So if you compare these equation I1, I2 with this equation I1 and I2, so in the place of y11, what is there? In the place of y11, you are having y11a plus y11b, and in the place of y12, y12a plus y12b. So similarly, here I have written that is y11 and y12 and y21 and y22. So which means in the case of y parameters also, if the two if the two networks are connected in parallel, then the equivalent network parameters are, you have to add the two network parameters, that is the admittance parameters of the first network, that is ya, plus the admittance parameters of the second network, this is yb. So this is not the normal addition, this is the matrix addition, because here the ya represents the admittance matrix of the network A, and here the YB represents the admittance matrix of the network B. Okay, so here this Y represents the admittance matrix for the equivalent network Y. Okay, so which means if you want to get these Y parameters of that equivalent network, then you have to add the two networks admittance parameters, then you will get the resultant network Y parameters. So like this, this is the parallel connection. So next, we are going to discuss about the cascade connection. So I think this video is going to end. Okay, so in the, I mean, after you rejoin, we will continue this cascade connection. Okay, so I'm going to stop here. Then you can rejoin again. Okay, so join very quickly. Okay.